Okay, so good afternoon everyone. Okay, so today I have thought of doing the experiment, but before doing the experiment on the PID controller, I first have to complete the portion of the theory, basically theory portion of the PID controller, because it was not completed. Okay, so I will first go through the theory portion. Okay, so then if time permits, then we will be continuing the experiment. Okay, otherwise we may continue the experiment in the next class also, because the experiment is a little bit lengthy. Okay, because you have to understand many things, because the practical explanation of a PID controller is given in the experiment, so it will help you to understand the PID controller in a better way. So till now we have discussed about the proportional controller. So we have seen that whenever there is a error in a system, okay, any disturbance in a system, so if there is a disturbance or error, so the output will not be equal to the desired input. So the feedback will sense that error. Okay, actually it will sense the output or measure the output, and it will send to the summation point where the input and output will be compared. So the feedback will convert the output into an equivalent signal, so that it can be compared with the input. Now over there, this summation point, it will create the error. So it will signal whether there is an error or not. Input and output signal are both equal, then there won't be any error. If there is a difference, so the error will be created or it will be indicated. So the controller has to take some necessary control actions, and their control action output will be fed to the actual system or plant. So the plant can make some necessary changes, okay, so that the output which it was actually delivering, it was not accurate because there is some error. So it will make some necessary changes so that it gives the output as per the requirement. Okay, so in this case, so in proportional controller we have seen that proportional controller is nothing but a gain, where some amount of gain is being multiplied, so which results in reducing some of the error, but it was observed from the equation that the error, okay, suppose if you take this particular system of a water level control, so it was seen from the equation that this was the output considering the error or considering the proportional controller. So Kp is the gain of the proportional controller. So if the feedback is 1, okay, that is unity feedback, and the this particular control system of the forward part control system, or this or actually you can say the actual plant, if it is K, the gain is K, then the output will be K into Kp by 1 plus K into Kp multiplied by input. So from this equation it shows that the input and output depends upon the value of Kp. So if the Kp is too high, then only output and input can be almost equal. So the proportional controller works in such a way that more is the error, more is the gain, so that the output can be reached towards the input and we can minimize the error. Okay, but it was observed that due to this, if the value of Kp is increasing, because suppose the error is increasing, the value of Kp is increasing, so it will result in excessive overshooting. Okay, and the system will take a lot of time to settle down, and most importantly, it will never be totally settled down. One second. Okay, so with the help of proportional controller only, the amplitude of the overshoot increases too much, and the system becomes means the settling time also increases. Okay, and most importantly, the steady state error is not always addressed, because initially if the error was like this, Suppose this was the input, okay, and the output was like this. Suppose second order system like this. So there was a error, okay, so there was a gap, suppose. So this gap is called the steady state error. Okay, this is the steady state error. Now with the help of the proportional controller, we have minimized that particular error, okay, but the error is not it is not totally zero, and the overshoot has increased. There is no problem. So what we have done, we have introduced the proportional plus derivative controller. So with the introduction of derivative controller, what happens? The derivative controller, when there is some rapid change in the you can say output, okay, or input rather, okay, so or any disturbance in the system, if there is a major disturbance in the system, then that disturbance can be addressed quite fast with the help of the derivative controller. That means derivative controller actually it gives a signal proportional to the rate of change of the error. That means in the water level controller, we have seen that if the tap from the bottom is open and water is running out at a faster rate, so what will happen? The proportional controller will produce the proportional you can say gain, but if the rate of decrease of the water is increasing, the rate is increasing, then proportional controller cannot help it over there. So it has to supply more and more magnitude of signal. So the overshooting will be huge. So it will result in unstable. So that means if the error is more and fast, then what will happen? The proportional controller will produce more value of Kp. So the Kp value, it will try to increase Kp as much as possible. It will keep on increasing, and if it keeps on increasing, this becomes huge. It can result in instability. Okay. So here the derivative controller comes into action. What it does with the help of proportional controller, it reduces this steep rise. Okay. It reduces the steep rise. That means if the rate of increase of the error or rate of change of or rate of rise of error is more, that means the error is generated with a higher rate, so it can remove that very easily. It will act according to the rate of increase of the error. Okay, so it will generate a signal which is KD, that is the gain of the derivative controller multiplied by rate of change of the error. Okay, so this will also not reduce the steady state error completely, but what it will do with the help of this, since it is acting very fast, so the overshoot will reduce. That means if the error was like this, suppose if the error is like this, okay, this is the error, this part, and with the presence of error, if you are using proportional controller, then it will try to neutralize the error, but the steep will be very high. But with the help of PD controller, what happens? With the PD controller, it will produce some magnitude, so the steep will be a little bit there, but due to the rate of action of the derivative controller, which is proportional to the rate of increase of error, okay, so it is acting as per the rate of increase of error, so it will not allow the overshoot to be too much. Okay, so it will minimize overshoot, and then it will try to stabilize it, but still the error will be there. Error will be there. Okay, this is the operation of a PD controller. So with PD controller, the output rises more rapidly towards the steady state value, and the overshoot is reduced. Because the derivative mode reduces the system oscillations, we can increase the proportional gain element to a higher values. Okay, but what will happen with this particular higher value? Okay, you can increase, and if you increase it to much more higher value, it will stabilize faster, but this total error is always there. Steady state error, there is the offset. This is also called the offset. Offset is always there. Offset means if this is your input, then output is like this. So there is some gap. This is called the offset. So it is not matching with the exact input. So this steady state error, that is creation of the steady state error, which is resulting in the offset, will also be there in PD controller. So what is the advantage then? In P controller, the overshoot was very high. It was trying to minimize, because without any controller, error is always very high. But with the controller, error can be reduced, but it cannot be reduced totally with the help of proportional controller. So, but in the action of controlling the error or minimizing the error, what the controller does, it increases the oscillation of the system, the overshoot of the system. That was disadvantages. So, to overcome that, PD controller is used. So, PD controller has the advantage, as since it acts upon the rate of increase of the error, so it reduces the overshoot. But the offset, it cannot reduce totally. Okay, this is the PD controller. Okay. Now coming to the PI controller, that is proportional and integral controller. Okay. So proportional plus integral. So what it does, it helps in reducing the offset. So what it does, it acts in such a way that it integrates with the error. It generates a signal which is proportional to the integration of the error. Okay, so the addition of an integral element to a proportional controller modifies the response, removing the offset and giving a steady state value the same as the input set value. That means it minimizes the offset. So if the input is like this, it will result in the creating the offset like this. Okay, not resulting in the offset, it will minimize the error totally. So no error is there. So with the help of integral controller, we can totally minimize the error. So the elimination of the offset is because the integral mode gives a controlling response which is proportional to the area under the error time graph up to the current point, and so it can give a controller output signal even the error has become 0. So that means if the error is 0, so you may say that the controller action will not required, so it will stop. So once it stops, again there will be error, because in P and PD controller, since the steady state error is not 0, so it will continue to operate. But in PI controller, when the error is become 0, then the controller, if it stops operating, then again the error will take place. That is why the PI controller is designed in such a way that it can operate even though error is not there. So it will keep on giving the same control action so that error becomes 0. Okay, so there are many situations where we require controller to continue giving an output signal when the error is 0. For example, the water level control. So if the outflow changes to a new rate, when the controller has to receive an error signal to maintain the water level constant and still gives a new flow rate. That means if the particular water level, okay, the water flow rate which is coming out, water flow, if it is increases, and if the controller keeps on giving the water flow rate at the same previous rate, then there will be error. Okay, so it will be able to control that also. Okay, so one thing to be noted is that PI controller tends to be used with the systems where load disturbances occur frequently. So where there is frequent disturbance, okay, rapid disturbance. So PI controller, one thing is very major difference between PD controller is that in PI controller, the time taken for the response of the controller is less, is more. It takes more time to respond compared to PD controller. So PI controller takes more time to respond, but when it responds, it can handle many huge amount of load disturbance, okay, with very smoothly, okay, with zero offset, zero steady state error. So that is why it is used for cases where load disturbance occur frequently. Okay. Now PI controller can be written in this particular equation. So the error signal will be equals that is the signal coming out from the PI controller will be equals to error signal plus the, or you can say I controller, integral controller, plus the K, that is the constant, and integration of this. Okay, and if you take the Laplace transform, this is represented in this way, which means that if I draw the block diagram, okay, this is the for a second order system. If I show you this simple block diagram, then you will be able to understand that suppose this is the input signal. Okay, input signal, this is the summation point. Okay, this is RS, and this is the error signal ES. Okay, this is plus, this is minus, feedback is coming. This is the I controller. Suppose this is the I controller, only I. Okay, so input is entering over here, and then we are getting this output EAS, which is going inside the forward path transfer function GS. So this EAS is nothing but what is inside this I. Inside the I is a KI, a gain, and whatever error signal is entering, it will be integrated. So if it is integrating the error signal, that means after Laplace transform it will be ES by S. So this is inside this particular I block. Okay, so this is inside the I block. Now there is a major difference that in terms of functionality, the PD controller is able to react fast to control the error signals changes and generate adequate countermeasures in terms of control signal. Okay, so PD controller is acting as per the requirement. It acts fast, very fast. This comes at a cost of decreased steady state performance. So since it is acting very fast with respect to the steady state error, okay, or fast to the error signal, okay, but the steady state performance is minimized. Okay, it is actually sacrificed. But PI controller, on the other hand, is relatively slow, and it reactions slow in its reactions to fast variations. However, can lead to significant improvement of the steady state performance. The steady state performance is increased. Okay, so it takes a lot of time. It takes much time compared to the PD controller. The PI controller takes much time, but since it is taking time and it is operating as per the integral of the error, okay, so its steady state performance is better. Now with the use of PID all the three together, okay, so what is the advantage? Advantage is that it will have the effect or the advantages of all the three simultaneously. That means with the help of first proportional gain controller, it will be able to increase the gain, okay, as per requirement. It will be able to increase the gain. So more is the gain, better is the stability. So if you increase the gain of the proportional controller, it will result in accurate result, more accurate result. But only proportional controller, if it is used, then there will be too much overshoot. So to minimize that, we add derivative controller to it. Derivative controller, what it is doing, it is minimizing the overshoot. Okay, so you can see now with the help of integral controller, the addition to the file proportional mode of integral mode removes the file offset and gives a steady state value. So integral controller, if it is associated with the derivative controller, because derivative controller alone cannot reduce the error, what it can do, it can minimize the wave over oscillation, okay, or you can say overshoot. So P controller will create a huge overshoot, D will try to minimize overshoot, and I will stabilize it totally or make the error 0. So the integral controller removes the file offset, that means the difference between input and output, the steady state error, and gives the steady state value, the same as the input set value, and the addition of the derivative mode allows the system to rise more rapidly to steady state value. So derivative controller will help you to reach the steady state value faster, but it cannot help you to reach the steady state value. It will accelerate the steady state, accelerate the response. The D controller will accelerate the whole system response, and I will minimize the error, and P will take you to that value where you can minimize the error. In more easy terms, suppose this is our system, this is our input, we are getting output like this. So first of all, what is required? It requires a push, an increase in magnitude. So the proportional controller will increase the magnitude, but only proportional controller will result in overshoot. So what we will do? Derivative controller will minimize the overshoot, but error cannot be minimized, so integral controller will minimize. So P controller is increasing the value of the gain, so it is jumping towards the output, and derivative controller will help to minimize the overshoot so that it reaches the steady state stability easily, faster. Otherwise, if overshoot is there, too much overshoot is there, so it will take huge time to settle down. Rather, if it takes less time to settle down, then you can get steady stability faster. So that is why derivative controller helps you to minimize the overshoot. ठीक है? प्रोपोर्शनल कंट्रोलर क्या करता है? वो वैल्यू को इंक्रीज करके आउटपुट की तरफ ले जाता है. अगर आउटपुट बहुत ही नीचे है, खराब है, तो मैग्नीट्यूड को बढ़ा के आउटपुट की तरफ ले जाता है. लेकिन अकेला अगर ले जाएगा तो ओवरशूट हो जाएगा और स्टेडी स्टेट स्टेबिलिटी बहुत बाद में आएगा. इसलिए डेरिवेटिव कंट्रोलर फास्ट एक्शन करता है और एरर को मतलब कि जो सिग्नल को ओवरशूट को मिनिमाइज कर देता है और स्टेडी स्टेट स्टेबिलिटी की तरफ जल्दी चला जाता है. लेकिन ऑफसेट रहेगा, गैप रहेगा, और गैप को मिनिमाइज करता है आई कंट्रोलर. सो इन दिस वे PID ऑपरेट्स टुगेदर. Okay, and this is the representation. You can see this is the equation. Suppose the gain is 1, and if the gain is k, suppose I want to mention the gain as k, suppose kp is the gain. Okay, so EA means the error signal which is coming out, a signal which is coming out from the controller, and E is error signal. So E is entering the controller, PID, this is PID controller. Okay, so it is entering that. So what is happening actually? It is equals to KP into error, okay, plus TD, that means another gain, or you can write KD also. That is the gain of the derivative controller, that is less compared to KP, but there is some gain. So gain of the derivative controller multiplied by the derivative of the error signal plus gain of the integral controller multiplied by the integration of the error signal. Okay. Okay, so after Laplace transform, you will get this by kind of a result. So it will be, if it is 1 1, if it is KP, only KP is there, plus derivative becomes STD plus integration becomes 1 by S, so KI 1 by S. Then the signal is sent to the actual plant. So now the plant will sense EAS. So error signal, if you give to the plant, it cannot do anything. It will act upon the input. But if you are changing the input and adding the control signal with the input, then only it can operate. Okay. Okay, then only it can operate. Now types of PID controller. Now the above mentioned PID control principle may be applied to many types of PID controllers, such as pneumatic PI controller, hydraulic PI or PID controllers, electronic PID controllers. So nowadays PID controllers can be developed in new types of PID controllers, such as the digital PID controller, fuzzy PID controller. So depending upon the applications and where we are using, there can be fuzzy controllers, there can be self-tuning PID controllers. Okay. So different type of PID controllers are there. So there is one numerical. We will discuss that later. First of all, I would go to the want to proceed with the experiment. Okay. So in your syllabus, there is experiment number 2, where you study the study of closed loop PI and PID controllers. Now what we will do, we will study PI, PD and PID all. Okay, because the syllabus only PI and PID is there, PD is not there, but we will also study PD. So this is just the brief introduction. See, this is the way it is represented in the block diagram. So error signal is there. So first there will be proportional controller. So KC is the proportional one. Then integral one is there. Then the derivative part is there. Okay, this we have already discussed. Now this is a PID controller, closed loop PID controller. Suppose for unity feedback, RT is input, YT is the output. Okay, and this is summation point plus minus negative feedback unity. This is plant transfer function PS. That means the total system, actual machine which is operating. Now this is the PID controller. So the controller will operate as per the error signal. Okay. Now the plant P is controlled by the input UT, which is represented as this. So UT is the input. Okay, this is in time domain. That means UT signal will enter the plant. What is UT? UT is the signal coming out of the controller, because the input to the controller is ET, error. The error is entering controller, PID controller. The PID controller will make some necessary actions, necessary changes. Okay, and it will act on it, and as per the requirement, it will produce the output of UT. Okay, so now the output UT, whatever actions the PID controller has taken, depends upon the error. So based on the error, PID controller is taking the action. So the output which the PID controller is giving you is actually the summation of all the 3 controllers individually, which they have acted on the error. That means the P controller will act on the error of its own method, I controller will act on the error by its own method, and D controller will act on the error by its own method. So P means it will just multiply some gain with respect to the error signal. So error is ET, KP is the gain of the proportional controller. So this is the signal which is coming out from the proportional controller. This is the signal which is coming out from the derivative controller. So KD is the gain of the derivative controller, and it will act on the error, rate of change of error. So it will be actually DDT of ET. DDT of ET. Okay. Plus Ki is the gain of the I controller, integral controller, multiplied by the integral of the error signal with respect to time. Okay. Now, if you where see Kp is the proportional gain, Kd is the derivative gain, Ki is the integral gain of the controller. Now, frequency domain representation of the PID controller. Frequency domain means in the S domain. Now, frequency domain, taking the Laplace transform of both sides, the control input can be represented as this. Because U was, if you see this one, U is the output, E is the input. So transfer function will be US by ES. That means US by E, because you take E common from here. If you take E common, take E common. So what you will get? Kp plus, okay, derivative of, okay, this one. So you cannot take E common from here actually. First you have to do the Laplace transform. So first of all, take the Laplace transform. So taking the Laplace transform, what we can get? It becomes US. Okay. Then Kp ES, then Kd SES plus KI ES by S. Now from here take ES common. Now you can take ES common. KP plus KD S plus KI by S. Okay. Now which is output? U is the output. So output by input. Okay. So output by input will give you this. Okay. Same thing. You have just calculated. Okay, so now this is your response. So thus the PID controller adds pole at the origin and 2 zeros to the open loop transfer function. So what it is doing, it is adding some one pole in the origin, okay, and 2 zeros in the transfer function, because this is an additional part. Because if PID controller was not there, then only E will be entering plant, but since UT it is entering plant, so it is actually ES into this one, ES into this. This is the additional part which is entering the plant. So what is the additional part? One pole at the origin, that is type 1, and 2 zeros at the of the open loop transfer function. Now the closed loop transfer function, this is the value of say US by ES. Okay, US by ES. Agree? Now this is the value of the transfer function CS. CS means this one, because इस इक्वेशन को ठीक से देखो, US equals to the PID controller transfer function multiplied by the error signal. So CS is the PID controller transfer function. So this is CS. This one is the CS one. This is CS controller transfer function. CS. CS के अंदर वो है. So now for the closed loop transfer function, closed loop transfer function, GS में मतलब GS मतलब फॉरवर्ड पर ट्रांसफर फंक्शन क्या है? CS into PS by 1 plus CS into PS, which is nothing but YS by RS, isn't it? Feedback है 1, unity feedback. Okay, feedback is 1. Okay, so the feedback is 1. So the closed loop transfer function, that is YS by RS, will be forward path transfer function GS. GS is nothing but CS into PS. So CS PS is the value of GS. ठीक है, हम लोग को तो पता है ना ये वाला चीज. फॉरवर्ड पर ट्रांसफर फंक्शन, क्लोज लूप ट्रांसफर फंक्शन जो होता है जिसका फीडबैक 1 होता है, वो होता है GS by 1 plus GS. ठीक है, HS 1 है, ठीक है, into 1. ठीक है, HS 1 है, तो इसलिए यह है क्लोज लूप ट्रांसफर फंक्शन. ओके, so this is the transfer function of the PID controller. Now this is the physical realization of the PID controller, how to represent it. क्योंकि पहले तो हमने सिर्फ ब्लॉक दिखाया PID, उसके बाद प्लांट. सो यहाँ पर ऐसा नहीं होगा, एरर ऐसा जाता है, प्रोपोर्शनल सर्किट में जाएगा, इंटीग्रल में जाएगा, डेरिवेटिव में जाएगा. ओके, देन टोटल सिग्नल ऐड होगा, पूरा समेशन है, फिर जाएगा US और फिर उसके बाद प्लांट PS. YS फिर फीडबैक है, ये वो समेशन RS. ठीक है, ये वाला देखो, ये जो था ये यहाँ पर हमने पीआईडी कंट्रोलर पीआईडी लिखा था, एक्चुअल होना चाहिए ऐसा, ठीक है। दिस इज द फिजिकल रियलाइजेशन ऑफ द पीआईडी कंट्रोलर। ओके, now why do we need a PID controller? So now see, if you take only P controller, so proportional controller, we have seen that it will have the effect of reducing the rise time and will reduce but never eliminate the steady state error. So proportional control क्या करेगा, वो rise time को reduce करेगा, ठीक है, मैग्नीट्यूड पे ऊपर फ्लो कर रहा है, so it will reduce the rise time but it will not reduce the steady state error. Integral controller, what it will do, it will, if you take only integral controller, then it will eliminate the steady state error, because integral controller has the capability of eliminating the steady state error completely. No other controller can do it completely except integral controller. But only integral controller you cannot take, because it will make the transient response worse. Transient response means the stability, okay, the transient response, that means the overshooting, okay, and the control will not be possible for only integral controller. Now derivative controller will make the effect of increasing the stability of the system, okay, it will increase stability by reducing the overshoot. Okay, so it will reduce the overshoot, but it will affect the rise time. So rise time will be very less, okay. The PD control, if you add P and D, so their advantages will be added, okay. So it will result in increasing the stability faster, it will reduce the overshoot and it will reach the steady state condition faster, but the steady state error will not be eliminated, okay, error will not be eliminated, so steady state response is not affected. If you take PI controller, so what will happen, it will eliminate the error, okay, but the settling time is increased. Settling time means it will take more time, because PI controller में क्या प्रॉब्लम होगा, अगर PI controller इस्तेमाल करेंगे तो डेरिवेटिव क्या करता था, डेरिवेटिव जो है वो ओवरशूट को कम कर देता था, लेकिन PI क्या करेगा, PI ओवरशूट को, मान लो कि ये इनपुट है, ओवरशूट को बढ़ा के रखेगा, एरर कम कर देगा, लेकिन द settling time will be increased, okay, settling time will increase, overshoot is more and settling time will also increase. You will keep on like this and then go, okay. That is why we need a PID controller. D controller जब भी देंगे तो ये settling time ऐसा नहीं होगा, settling को कम कर देगा, ऐसा कर देगा, overshoot कम करेगा, overshoot कम करने से oscillation कम हो जाएगा और बहुत पहले स्टेबल हो जाएगा। और सिर्फ D अगर इस्तेमाल करते हैं तो एरर जीरो नहीं रहेगा, आई करेंगे तो एरर जीरो रहेगा, लेकिन सेटलिंग टाइम लगा देगा, इसलिए दोनों को एक साथ करेंगे, प्रोपोर्शनल के साथ तीनों को एक साथ, फिर जाके सिस्टम एकदम से स्टेबल होगा। बट अ पीआईडी कंट्रोल रिमूव द स्टेडी स्टेट एरर एंड डिक्रीजेस सिस्टम सेटलिंग टाइम्स व्हाइल मेंटेनिंग अ रीजनेबल ट्रांजिएंट रेस्पॉन्स। So it will minimize the error, so removes the steady state error and decreases the settling time. Settling time also decreases and maintains a steady transient response. Suppose we take a very basic example, okay, to illustrate a controller of PI, PD and PID controller in Matlab. First of all, we will take a basic system, open loop system, and then make it a closed loop system. Okay. Suppose we take this particular mass, spring and dashpot example. it is connected to this particular ground, and we are pulling it. So if it pulls, it will be moving. Okay, so this is a physical system. The force is equals to mass into acceleration plus the friction is there. Okay, so more force is required to overcome this force also of dash force. So V into rate of change of displacement, that is velocity, plus the spring. So more force is required to pull the spring also. So see, spring constant. So this is the dashpot constant, this is spring constant multiplied by distance equals to force. Okay, so this is the time response of the force equation of this physical system. Now for the frequency response, for transferring into Laplace transform, converting into Laplace transform, taking the initial condition 0, so it will become the double derivative will become x square m s square xs plus b derivative will become s. So s xs plus k xs equals to f. F is the output, f is the input, x is the output. Why? Because we are pulling it, we are giving some force, then only you are getting the displacement. So f is the input and displacement is the output. Okay, so xs by fs is the transfer function, open loop transfer function. Okay, it is 1 by m s square plus bk plus x k. Suppose the mass is m is 1 kg, the dashpot constant is coefficient is 10 Newton second per meter, and the spring constant is 20 Newton per meter. So just replacing the values of m, b and k, so it becomes 1 by s square plus 10s plus 20, which is the open loop transfer function. It is a second order type 0 open loop transfer function. Okay, now for the Matlab code, suppose we want to see the output response. So if you put this particular Matlab code, you will get this output response. Okay, this is a response. Okay, so remarks is that the DC gain of the planned transfer function is 1 by 20. Okay, so 0.05 is the final value of the output to a unit step. Now what we are actually doing, this is the code of what we are doing. You see, the code is step function. That means if I simplify, this is the transfer function, this is the system which you are putting. That means we are taking a system, okay, where the system is this one, 1 by s square plus 10 s plus 20. Okay, this is the output, this is the input. Suppose rs, this is actually say xs, sorry, fs is the input, fs by xs. Okay, so what input we are giving? We have to give some signal, isn't it? We have to give step signal, ramp signal, parabolic signal, impulse signal, otherwise you will not get any output, because this is the equation, this is the transfer function. So after giving this step input, we will get this curve. Step means unit step, because we Matlab we know this is nothing but unit step. Let us see in Matlab. Okay, before Matlab opens, tell me, have you understood this particular portion of PID controller? What are the differences of PI, PD and PID? ये वाला जो था, this one, this is very important. Okay, because derivative controller will help you to act upon the rate of change of the error. So it will minimize the overshoot. So it will stabilize faster, increase the stability, but it will rise time will be very less. So proportional controller is used for that, to increase the rise time, but steady state error will not be reduced. So integer controller reduces the steady state error. And if you take both PID all together, then advantage is that you will get perfect output with steady state error 0 and with very less overshoot. So I'm opening the M file. Okay, now I'm taking the Matlab code. Okay, so this is, I'm naming it as output response of the open loop system. This is comment. Okay, I'm saving it. I'm saving it in some other file. Okay. Suppose in desktop I'm creating a file. Experiment PID. I'm naming it PID 01. Okay. A name should be given in such a way that it does not clash with the function, because we know that there is some command function. Okay, suppose TF, help TF. TF is a function of the Matlab. If you name any file, M file, with TF, so what will happen? It will clash with it. So it will create some error. That is not good for the Matlab. Okay. Now what I'm doing, I am just writing the transfer function over here. So the transfer function I will get in this way in the output. Okay, 1 by s square plus 10s plus 20. Now if I want to see the output response with the step signal, unit step signal. Okay. Sorry, s is small s. Small. Okay, so it created a signal. So you see, this is equal to this, same thing. Now we have given step signal as input. Now what is the value we are getting? So if you see that, sir, it has reached steady state, it is giving a straight line, but see what is the value. If I say the axis y level, oh sorry, wait, if I write in this way, wait, x level axis starting from 0 to 5, then from 0 to 1. Now see, what was the input? Input was unit step. तो इनपुट इज दिस लाइन, दिस शुड बी द इनपुट. इनपुट यहाँ है, आउटपुट कहाँ है? एकदम नीचे. कितना गैप है? 95% एरर, बिकॉज द आउटपुट विच यू आर गेटिंग हाउ मच? 0.05 and input is 1. It is 20 times less. See, the DC gain of the plant function is 1 by 20. That means is the final value of the output to a unit step input. This corresponds to a steady state error of 0.95, quite large indeed, 95% error. Furthermore, the rise time is about 1 second and the settling time is 1.5 seconds. Rise time is about 1 second means rise time किसे कहते हैं? 100% रीच करने पर rise time, मतलब 100% उसका maximum value. So rise time is around 1 rise time, that means up to here, okay? Rise time up to here, not 90%, rather 90%, so up to here 1 second, और settling time जा रहा है 1.5 second. Settling time is 1.5 seconds. If you see, that is why it is taking quite time. So it is, see, it is settling time is 1.5 second, rise time is 1 second. देखो, rise time 1 second, settling time 1.5 second, huge. So it cannot be used. It's a very bad system. So what we will do, we will use some controller. First control क्या करना है कि since the error is 95% error, 0.95, so first of all you will use some proportional gain. So पहले क्या करेंगे, प्रोपोर्शनल कंट्रोलर यूज करेंगे, प्रोपोर्शनल इनपुट दे देंगे प्लांट को, सिस्टम जो हमारा है उसको एक प्रोपोर्शनल गेन को मल्टीप्लाई करेंगे. ओके, so the transfer function of the control system is then US. Okay, that is the transfer function of the control system. Okay, so so this is the US input to the plant. Now अभी क्या करेंगे हम लोग, इसको क्लोज लूप सिस्टम बनाएंगे. फीडबैक इज 1, यूनिटी फीडबैक is 1. we're making it a closed loop system. Okay, so after making it a closed loop system, this is the proportional controller, okay, which is coming, and we are giving the input signal, and output we are getting US. So US equals to KP into ES और CS equals to KP. CS मतलब इसका जो ट्रांसफर फंक्शन जो हमने देखा पहले कि PID के लिए CS लिखा था, अब इसी P कंट्रोलर यूज कर रहे हो, तो इस जो कंट्रोलर को यूज कर रहे हैं इसका ट्रांसफर फंक्शन है KP, क्योंकि KP इटसेल्फ, बिकॉज क्या है, US बाई ES होगा. अभी US जा रहा है तो पहले क्या था, ES अगर सिर्फ प्लांट में जाता तो we will not be able to control it. So we have to multiply the gain with the error. So gain into error is giving the controller input. So the closed loop transfer function of this spring mass system with a proportional controller is this one. So what we are doing, we are just multiplying it. So ऊपर क्या होगा, KP ऐड हो गया. तो पहले क्या था, पहले था हमारा ऐसा है ना, XS by FS. तो यहाँ पर अगर हम KP को ऐड करेंगे, तो क्या हो रहा है, KP ऐड करने से ट्रांसफर फंक्शन तो ऐसा डायरेक्ट होगा नहीं, क्योंकि ये क्लोज लूप ट्रांसफर फंक्शन बन गया. तो भी क्या होगा, ये KP है, ये मान लो कि ये GS है, तो अभी GS इंटू KP बाई 1 प्लस GS इंटू KP. ठीक है, इसको सॉल्व करेंगे तो फिर GS इंटू KP मतलब के KP मतलब CS है यहाँ पे, और P है इसका GS. तो आफ्टर सॉल्विंग इट वी विल गेट KP बाई S स्क्वायर प्लस 10S प्लस 20 प्लस KP. आफ्टर सिंप्लीफिकेशन, if you do it you will get this particular solution. Now this is our transfer function. अब ये ट्रांसफर फंक्शन हो गया, अब इसको डिफाइन करना है. अब KP का वैल्यू क्या है, KP तो वैल्यू होना चाहिए. मान लो KP है 500, बहुत ज्यादा, क्यों, क्योंकि 95% एरर है, तो KP मान लो 500. तो क्या करेंगे, KP को अगर हम डायरेक्टली यहाँ पर ट्रांसफर फंक्शन बैठा देंगे कि 20 प्लस 500 मतलब कि 520 और यहाँ पर 500, तो हम लोग ऐसा भी लिख सकते हैं ट्रांसफर फंक्शन को कि 500 बाई एस स्क्वायर प्लस 10s प्लस 520. So you will model the transfer function like this, equation like this. ठीक है, न्यूमरेटर ये यहाँ पर लिखेंगे 500 1 10 520. Okay, then also we can see what happens adding 500 1 10 520. Okay, we are getting this signal. This is actually equal to what we are supposed to get. but we will not use this. Why? Because we will use the actual syntax of PID controller. PID controller का syntax ऐसा है कि we use a function called PID. PID is a function in MATLAB. ठीक है, function in MATLAB. तो syntax क्या है देखो, KP को define कर रहे हैं हम लोग, एक constant है, KP is equals to 500. Then C is another variable equals to PID KP. That means the PID KP is stored in C now. Okay, stored in C now. Now what is the transfer function? Transfer function is this. ट्रांसफर फंक्शन जो है वो पूरा जो पहले ट्रांसफर फंक्शन था हम लोग का आ गया, हाँ ये है जी, तो जी को हम वैसे रख रहे हैं, यहाँ पर जी को भी लिख सकते हैं हम लोग। एक काम करते हैं, यहाँ से ये कॉपी करके ठीक है, और यहाँ पर कोई ज़रूरत नहीं है, ठीक है, ये वाला मैं अभी दिखाता हूँ क्या है, फिर कन्फ्यूजन क्लियर होगा। पहले देखते हैं कि व्हाट इज PID। सी PID इज अ फंक्शन, PID क्रिएट अ PID कंट्रोलर इन पैरेलल फॉर्म। PID पैरेलल फॉर्म मतलब ये वाला पैरेलल, 3 पैरेलल में है PID ऐसा। So it is creating a PID controller in parallel form where KP plus KI by S plus KDS by TF into S plus 1। अब syntax जो है, syntax ऐसा देना चाहिए, system that is a variable equals to PID K then KP KI KD then transfer function, ठीक है, ऐसे देना है। तो मान लो कि हमने सिर्फ यहाँ पर KP दिया है फर्स्ट वैल्यू, तो जो भी हम लोग वैल्यू पहले देंगे वो ट्रांसफर फंक्शन उसको लेके बैठ जाएगा कि पहला है। अगर हम लोग यहाँ पर मान लो कि सिर्फ डेरिवेटिव देना चाहते हैं तो यहाँ पर दे देंगे, डेरिवेटिव को देंगे ऐसा, यहाँ पर क्या है PD, अच्छा किसी डेरिवेटिव तो नहीं होगा, मान लो कि PD है, PD को क्या करेंगे हम KP 0 KD, क्योंकि PID 3 एक साथ लेगा, P पहले लेगा फिर I लेगा फिर D लेगा। If you want to use PD and you don't want to use I, so leave this middle term 0. If you want to use PI, so you will write KP, bas, third one you don't have to write, it will automatically understand। Okay, so now we are dealing with this particular case, okay, only P controller, so we will use only PID KP, means first variable, इसको हम यहाँ पर 500 भी लिख सकते हैं, कोई प्रॉब्लम नहीं है। तो ये क्या होगा, मतलब कि PID कंट्रोलर इस्तेमाल कर रहे हैं यहाँ पे, okay। So now over here we can directly use transfer function। So what we will do in this case, our transfer function is G, isn't it? G is our transfer function। So we will take this, okay, now we will not use step over here, G is our transfer function, okay। So now the MATLAB code is that KP, so first we will define KP। So what we are doing, we are adding the proportional controller, KP को add कर रहे हैं हम लोग, okay। Now C equals to PID KP, C equals to PID KP, okay। Now PID KP, so हाँ यहाँ पर डायरेक्ट भी इस्तेमाल कर सकते हैं हम लोग, 0 0 लेट मी सी इंटू, अच्छा लेट मी सी लिखा था कि नहीं, 0 0 G, ठीक है। तो हम लोग एक एक करके करेंगे, जैसा अभी यहाँ पर दिखा गया है कि ट्रांसफर फंक्शन जो है वो ऑलरेडी हम लोगों को डिफाइन किया गया है G करके, तो हम लोग वापस नहीं करेंगे, ठीक है। अभी क्या है कि ये जो ट्रांसफर फंक्शन डिफाइन किया गया था ये सिर्फ ये वाला ट्रांसफर फंक्शन है, यहाँ पर पी एस है, वो पहले हमने जी लिया था, ठीक है ना, इसमें जी लिया था जी। सो ये जो जी है इसके साथ के पी मल्टीप्लाई होगा, सो के पी इंटू जी, but kp is not multiply. What we are multiplying? We are multiplying the signal us. Sorry, kp. Actually, yes, we are multiplying kp. So kp is the multiplication. So kp is not your transfer function. Transfer function is PID of kp. So c is the PID of kp. Okay. So c is the PID of kp. So we will multiply the transfer function with pi. Okay. तो फिर इसको ऐसा करेंगे हम लोग, ट्रांसफर फंक्शन, टोटल ट्रांसफर फंक्शन इज जी। आई एम रिपीटिंग वंस अगेन, ट्रांसफर फंक्शन जी इज द ओपन लूप ट्रांसफर फंक्शन, विद दैट वी आर मल्टीप्लाइंग द पीआईडी ऑफ द फॉरवर्ड पाथ ट्रांसफर सॉरी पीआईडी ऑफ द प्रोपोर्शनल कंट्रोलर। So PID of the proportional controller, that transfer function is saved in C. So C is the value of the PID KP. So PID KP multiplied by G is the forward path transfer function. This one. PID KP into G is the forward path transfer function and feedback is unity. So total transfer function will be T equals to feedback C into G into 1. C into G comma 1. So if you do over up to here, then you will get this particular solution. You see, this is open loop transfer function G, this is KP, P only controller, okay. Then we are getting 500 is added or multiplied, this one, KP is multiplied, okay. Now if you do this step, or if you write this step equation over here, step function over here, step of T होगा अभी, ठीक है। तो these are result. So previously what was the result? अभी क्या करेंगे, इसको दोनों को रखेंगे, ठीक है, रखेंगे, इसको रेट करेंगे, रेट होल्ड ऑन कमांड देंगे जाके वो ना उड़े। अच्छा, ठीक है, अलग कलर हो गया। देखो पहले क्या था, पहले ये वाला था ब्लू वाला, अभी पी कंट्रोलर देने से वो 1 के करीब चला गया, 500 दिया। तो अगर मान लो इसको 1000 देते तो क्या होता है, देखा ज्यादा स्टीप हो रहा है। तो देखो इफ यू concentrate over here, see the settling time is just after 1, okay, suppose 1.25, ठीक है, इसको हम 500 रखते हैं। देखो ये अब भी सेलेक्ट टाइम वही है, लेकिन पीक जो है वो पीक कम हो गया है। यहाँ पर देखो पीक जो था वो पीक बढ़ गया, 1.6 के चला गया और lot of oscillations were there. Now if you reduce to 100, okay, so you will see you are getting better result, okay. But we will take 500, okay, because with the help of D and PI and I controller also we have to take the actions, okay. So that is why once again let me see over here, the rise time, the peak time is less than 0.5, and if I take 500, हाँ, दिस इज द रीजन, यहाँ पर एक कारण है। देखो अगर हम 100 लेते हैं तो प्रॉब्लम नहीं है, ऑसिलेशंस कम है, ऑसिलेशंस कम है, देखो। लेकिन यहाँ पर जो पीक टाइम है ये वाला, ये पीक टाइम, ठीक है, कितने सेकंड में ले रहा है, एम्पलीट्यूड 1 जहाँ पर है, टाइम इज 0.322 seconds, okay, 0.322 seconds. Now if I take 500, ऑसिलेशन इंक्रीज कर रहा है, लेकिन पीक टाइम जो है वो कम हो गया, ठीक है, 0.138। अगर इसको 138 अगर 1000 लेते हैं तो और भी कम होगा 0.101। बट डिसएडवांटेज ये है कि ज़्यादा अगर मैग्नीट्यूड लेंगे तो क्या देखा था कि एरर जल्दी जल्दी मिनिमाइज हो रहा है, लेकिन अगर ज़्यादा लेंगे तो ऑसिलेशन बढ़ जाएगा, सो ओवरशूट विल इंक्रीज, सो वी कैनॉट टेक टू मच ओवरशूट, सो वी हैव टू टेक अ वैल्यू which we can control at the end. So it was tested that 500 was good, not the optimum, not the best, but it was good. Okay, but still we can see some error रहेगा यहाँ पे। There is some error, you can see this is called the offset। देखो डॉट डॉट जो लाइन है वो है इनपुट का और ये है आउटपुट का, तो मतलब अभी तक एरर जो है वो है, लेकिन 95 तो नहीं है, 95% तो नहीं है, 0.5%, 0.3% है। So this is the with the help of the P controller. Now we will see PD controller, then we will leave the class and then we will continue in the next class. Okay, we will end the class over here. So what is the conclusion? Conclusion ये है कि the step response of the system in the Matlab indicates that the proportional control reduces the rise time. Rise time is reduced क्योंकि पहले क्या था, पहले देखो rise time 1 सेकेंड ले रहा था और सेटलिंग टाइम 1.5 सेकेंड। अभी rise time क्या है, rise time बहुत कम हो गया, 1 सेकेंड से कम हो गया। ओके 0.138 देखा था ना, 138, but increases the overshoot, reduces the steady state error but never eliminates it completely. So it has reduced the steady state error, it is not 95% anymore, it is less than 0.5% or 5%, but it does not completely reduces it. So you will see one more example of PD controller. In PD controller we will add the derivative controller along with the P proportional controller. So for derivative control action, the activating signal consists of proportional error signal added with the derivative of the error signal. So this, we know this equation. Okay, this is entering that particular plant. Okay, so a proportional plus derivative controller has the transfer function of Kp plus Kds. So proportional derivative control considers both the magnitude of the system error and the derivative of its error. Okay, that we know that it is controlling the magnitude as well as the derivative of the error based on the derivative of the error also. So derivative control has the effect of adding damping to a system. So the overshoot which was there will be reduced and has a stabilizing influence on the system response. So closed loop transfer function will be, now in this case it will be it is now Kp plus Kds. So Cs is Kp plus Kds, so Cs into Ps. So transfer function will be Cs Ps by 1 plus Cs Ps, actually this is Ps. This is Ps, okay, this is Cs Ps. So the particular transfer function, if you solve, it will be Kds plus Kp by s square plus 10 plus Kds plus 20 plus Kp. Suppose since we have taken Kp as 500, we take Kd as 10. What will happen? It will become 10s plus 500 by s square plus 20s plus 520. Because we don't take derivative constant or gain too much high. Okay. We will write the Matlab code. Now see, we will take Kd as a term. Now you will take PID. See, since it is PD controller, so we will take P controller variable Kp comma 0 comma Kd, because I we are not taking. So this is the syntax, and we will do the same thing as previously. Okay. So what we will do? We will just copy this one, this part. We will copy this part. Okay, we will paste over here. Wait 1 minute. We will do in a different way. Suppose it is CP, suppose. Okay, now we will take this one as PD. Okay, this is suppose TP, and this is TPD, because I want to see all the three together. Okay, so इसको हाइड कर देते हैं हम लोग. तो KP रहा, KD रहा, इसको पहले देखेंगे. अच्छा, TPD, हाँ ठीक है. इसको पहले देख रहे हैं. ये वाला था, ये वाला आया है. तो पहले क्या था, अगर तीनों के एक साथ देखेंगे तो see this is of different color चेंज तो अच्छा होता है. ठीक है, और नीचे वाला देखो, नीचे वाला है नॉर्मल, ठीक है, जिसका एरर है 95%. जो बड़ा वाला है वो है सी पी कंट्रोलर. ठीक है, अब देखो सेटलिंग टाइम ऑलमोस्ट एक है, बड़ा वाला और छोटा वाला ऑरेंज है, बड़ा छोटा वाला येलो है, बड़ा वाला ऑरेंज है. लेकिन द सेकंड वन यू कैन सी द ओवरशूट हैज रिड्यूस्ड, इट हैज बिकम डैम्प्ड, सो इट इज सेटलिंग टाइम इज लेस. Yes, settling time is less, so it is taking more time to, previous one is taking more time to settle, but the later one is taking very less time to settle. If you see over here, if you consider these to be the settling time, this one is settling time, this one. TPD, okay, TPD we have seen. This is TPD and this is TP. Okay, so it is almost above 1. It is almost above 1. Okay, so by comparing this, we can conclude that without integral there is type 0 system, and hence it will be finite steady state error to a unit step input. So steady state error is there. Without integral will not eliminate steady state error. Error will be there, but derivative controller reduce the overshoot and the settling time. So settling time has reduced, overshoot has reduced, and had a small effect on the rise time and steady state error. The PD controller has decreased the system settling time considerably. However, to control the steady state error, the derivative controller KD must be high. This decreases the response time of the system and make it susceptible to noise. If you want to increase the gain, suppose we increase the gain by 100. Okay, so you can see it is becoming very much stable. See कैसा फ्लैट हो गया. ठीक है, इसको गेन इंक्रीज भी कर सकते हैं as per requirement. Okay, but that will be too much, so you will not use that. Okay, so now we have understood that from the comparison that what is the difference between P controller and PD controller. For only P controller we will have a huge overshoot and long settling time. With use of PD controller we will able to reduce the overshoot and also the settling time. Okay, have you understood P and PD? Because PI and PID we will continue in the next class. Is it okay? Do you have any question? Have you understood? Hello, am I audible?
Yes sir, yes sir.
अभी समझ में आया ना मैटलब में कैसे देखते हैं हम लोग. नॉर्मल एक कंट्रोलर के बिना कैसा एरर है और पी कंट्रोलर के देने से कैसा एरर को मिनिमाइज कर रहे हैं, और फिर पीडी देने से हम लोग को ओवरशूट जो है वो कम हो गया, मतलब डैम्पिंग आ गया थोड़ा सा, और सेटलिंग टाइम भी कम हो गया, लेकिन पूरा एरर जो है वो जीरो नहीं आया है. अब पीआई देने से क्या होगा और पीआईडी देने से क्या होगा वो हम लोग नेक्स्ट क्लास में देखेंगे. ओके, Okay, so if you don't have any further questions, then I can end the class up to here. Okay, we will join in the next class.
Thank you, sir.
Okay.